So now we have 1 is the sum of all the probabilities. So 1 is equal to pi 0 plus pi 1 plus pi 2 plus pi 3, etc. We can factor out a pi 0 from each of those terms because all the terms can be expressed in terms of pi 0. So when we factor out the pi 0, from the first term we get a 1. From the second term, namely pi 1, we had pi 1 in terms of pi 0, and we had pi 1 was equal to lambda over 0, lambda sub 0 over mu sub 1 pi 0. So we factor out the pi 0, and we have lambda 0 over mu 1. Pi 2 we also expressed in terms of pi 0, and when we factor out the pi 0, the term that's left is this lambda 0 lambda 1 over mu 1 mu 2. And we can keep on doing this the next term, the next term, the next term. So what we've done here is we've factored out pi sub 0, and we have an expression in terms of the lambdas which we assume that we already know. So we can actually solve for pi 0. It's going to be 1 over the sum of that series. I will go a little bit farther, but before I do that, let's actually look at something that is equivalent to the state diagram, but it looks a little different. And that's something that's called the rate matrix. Sometimes it's called the infinitesimal generator, and sometimes that's called the kernel of the process. And we usually use the letter capital Q for this rate matrix. And along the vertical axis of the matrix, 0, 1, 2, 3, those are the states, those are the initial states. And along the horizontal axis, 0, 1, 2, 3, etc., those are the end states. So we're going from the initial state to the, I guess the next state would be a better way of saying it. And along the super diagonal, not the diagonal, but one line just above the diagonal. So if we're going from state 0 to state 1, that would happen at rate lambda sub 0. If we're going from state 1 to state 2, that would happen at rate lambda 1. From state 2 to state 3, that would happen at rate lambda 2. So we see along this super diagonal we have lambda 0, lambda 1, lambda 2, lambda 3, etc. Similarly, if we're going from state 1 down to state 0, that would be at rate mu 1. If we're going from state 2 down to state 1, that would be going at rate mu 2. And so along the subdiagonal, mu 1, mu 2, mu 3, and it keeps on going that way. Basically everything else is a 0, except on the diagonal. The diagonal is set up in order to make the rows, every row has to sum to 0. So in the first row, the only non-zero element we had was lambda sub 0, and if we want the whole row to add up to 0, then on the diagonal we need a minus lambda sub 0. Row that corresponds to state 1, we had lambda 1 was a positive term, mu 1 was a positive term. To make the row add up to 0 on the diagonal, we have to put a minus lambda 1 plus mu 1. And similarly for the row corresponding to state 2, corresponding to state 3, etc. The rows have to add up to 0. As mentioned, the rows of the rate matrix must sum to 1. Every row must sum to 0, excuse me. Q is referred to as a tridiagonal matrix. The non-zero elements are on the diagonal, the superdiagonal, and the subdiagonal. Everything else is 0. So there's just those 3 places. Hence, we refer to the matrix as a tridiagonal matrix. A simple example of a birth and death process that fits into this kind of category would be an MM1 queuing system. The first M stands for memoryless, which means that the inter-arrivals are exponentially distributed. The second M stands for memoryless, which means that the service times are exponentially distributed. The 1 refers to the fact that you have a single server in the system. So if we look at the state diagram, beginning with state 0, we can go to state 1, and we're doing that at rate lambda. That means that's the arrival rate. We can go from state 1 to state 2. Again, the arrival rate is still lambda. It's not dependent on, in this case, it's not dependent on the state. And similarly, we can do that from 2 to 3, etc., 3 to 4. Going the other direction, if we had, for example, 2 customers in the system and we had a service completion, and the service rate is mu, we would drop from state 2 to state 1. Similarly, if we had a service completion and we were at state 1, we drop down to state 0. And from 0, we can't drop any lower, so the only way to leave 0 is for an arrival to show up. So our rate matrix in this case looks a little bit nicer than it did before, because on the superdiagonal, everything is a lambda. On the subdiagonal, everything is a mu. And on the diagonal, we have to set the diagonal elements so that the rows all sum to 0, which means every entry on the diagonal will be a minus lambda plus mu, minus lambda plus mu, except for the very first row where the entry would just be a minus lambda. That would make the row sum to 0. Okay, so we're going to use this in order to compute the limiting probabilities pi sub I. Again, the sum of the probabilities must be equal to 1. So 1 is pi 0, pi 1, pi 2, etc. We can factor out the pi 0. What we're left with is a 1 plus, and again, pi 1 is in terms of pi 0, and the coefficient would be lambda over mu. Pi 2 we can get in terms of pi 0. The coefficient would be lambda over mu and another lambda over mu. In other words, a lambda over mu squared. Similarly, pi 3 we can get in terms of pi 0, and the coefficient would be lambda over mu cubed. And if you looked at this series, this happens to be a series we can add. We can't always add the series. They may be very complicated. But in this case, it's not particularly complicated. It's just a geometric series. We know the sum of a geometric series. The formula is usually a over 1 minus r, where a is the first term, which in this case is a 1. The common ratio to go from one term to the next would be lambda over mu, so 1 over 1 minus lambda over mu. And if we cross multiply to solve for pi 0, we get pi 0 is 1 minus lambda over mu. And once we've got pi 0, we can get pi 1, pi 2. We can get everything in terms of pi 0. Pi 1 is lambda over mu times pi 0. So we just get this kind of expression. And similarly, we can get lambda 2 and all the other lambdas. And here is lambda 2 in terms of pi 1 and pi 1 in terms of pi 0. So we're going to end up getting lambda over mu squared times 1 minus lambda over mu. And in general, pi sub I is equal to lambda over mu to the I times 1 minus lambda over mu. We actually recognize the form of this. If that was a p instead of a lambda over mu, we might look at that and say, that looks like a geometric distribution. So, and in fact it is. There are two different forms of a geometric distribution. This would be one of those two forms. Okay, so this is a particularly nice, easy example of a birth and death process. And there are many, many special cases of these.